here, correct? This class might have even gotten a little far. Did we get? No, we did not get through this slide. Did we?
Into the rectangles. You just kept saying more rectangles.
Got a fever? The only prescription? More rectangles, right? Yeah. Okay. So let me check the indices here. All right. So here's the essence of this lesson. Now this is a stepping stone to get us to definite integrals. We'll get there by the end of today. All right, which is exciting. We're building towards the definition of a definite integral. So we talked about x sub k's being your change in x, and your f of c sub k being a specific y value at c sub k. That's just notation. If I said what's f of 5, you would say plug 5 into the independent variable into the f of x function. If I say what's f of c sub k, you take c sub k, which is an x value, you plug it into the f of x function, and that is the height that we're going to use for that interval. Would you agree? So what's delta x sub k? Well, it's the width. It's the width of this interval. Now, what if k is 3? K was 1 for the first rectangle. K was 2 for the second rectangle. K was 3 for the third rectangle. How many rectangles are there based on this? K starts at 1. K goes up to, I'm on the third one, but I'm going up to the nth rectangle. What's n? The number of rectangles. They have to tell you. 1,000? 10,000? 100,000? Infinite, right? Aren't we heading towards infinitely many rectangles? Okay, well, wait a minute. Let's think about this. What's happening if, as the number of rectangles increases, there has to be a rule. Are all of these rectangles the same width? We don't know. All right? What does this thing mean? Well, did we write that down? Did we write down any notation, like what this means? What does that mean?
The norm of the partition.
Very good. The norm of the partitions. The largest rectangle. The largest rectangle. By largest, I mean widest. That's probably a better description. The widest rectangle. All right. Does that make sense? Do I need to rewrite it, or does that make sense? Widest rectangle. Well, wait a minute. So I have a choice here. I can make as many rectangles as I want. So guess how many rectangles I'm making on this interval? If I have choices. I have to do this by hand. 1. I'm only making 1 rectangle from here to here. Why? Because I don't feel like making 1,000 rectangles if it's the same area as 1 rectangle. It's busy work. With me? But when the graph grows steeply, if that's a word, I'm going to make more rectangles. Do you agree? The steeper the graph, the more rectangles I need. This is all theory, by the way. We're not actually going to do this. What does this mean again? The norm of the partitions approaches 0. Wait a minute. The widest rectangle, the width, approaches 0. What has to happen with the number of rectangles? Stay with me here. What has to happen to the number of rectangles if the widest one approaches a width of 0? The space gets filled with more rectangles. Oh, good. That's what we wanted, right? If we make the widest rectangle approach 0, the number of rectangles approaches infinity. me say it again. If the widest rectangle approaches 0, the number of rectangles has to approach infinity to fill the space. You with me? This is exactly what we want. Ready? Base times height. What happens when you get a base times a height? Area of the rectangle. And if you add them all up from the first to the last, and infinitely many of them, right, to the last one, if that exists, and make the widest one go to 0, that's just a recipe for getting the exact area under the curve, isn't it? That's good. That's exactly what the definite integral is, and that is a numerical value called I. It's a number. So next is the existence of definite integrals. Now, as you write this down, I want to kind of flash back to what it must have been like to discover this. All right. Now that I don't want to spend too long on this, but imagine being Newton or Leibniz and saying, I can find like an approximate area under the curve, like with rectangles. But is that the best I can do? Like, it is an approximation the best we can do, because all we've ever dealt with is geometric figures. Rectangles, maybe trapezoids, to try to get closer and closer and closer. But is there a true value? Is there a true value of the area? Or can I just get close to it, right? I mean, isn't that a logical question? And what this is saying is all continuous functions are integrable. What does that mean? The area can be calculated. Okay? Area integrable. The area can be calculated. What's the requirement to have area? The function must be continuous. Smooth? No, just continuous. Differentiable? Smooth and continuous. You can't have a slope at a sharp point, right? Integrable? Continuous. You can have area under a sharp point. Make sense? Ready? Area. You can have area under this thing. It's called a triangle. Right? You can have area. It's integrable. It was continuous. Ready? Open circle. No longer area. Can't have an area if there's an open circle. You can't find the area under that section of it. It wasn't continuous, right? Only requirement to find a definite integral is that the function is continuous. All right, well, let's take our second to last stepping stone. All right. If we make the norm of the partitions go to 0, there's another way to write that that's a little more concise. This is the limit as n goes to infinity. So guess what? No more norm of the partitions. If it's kind of a waste of time. If we're making the widest rectangle go to closer to 0 and we're filling the space with a ton of rectangles, infinitely many rectangles, does it really matter how wide they are? We might as well make them all the same width. So how many rectangles are there? N. Approaching infinity where they're all the same width, we're going to still sum up from k equals 1 to n. We're still doing a base times a height, f of c sub k, times delta x, and that equals I. So now all of the delta x's are b minus a over n. They're that width we found way back in the previous section. B minus a over n. Are you with me at all? The way they're going to ask these is, they're not going to ask you to find the area this way. There's not. They might say find a Riemann sum like we did in the previous section, find a right Riemann sum like Riemann sum midpoint. They're not going to ask you to solve for area this way. They are going to ask you multiple choice questions like what could have been the function if, and they'll give you a setup that's kind of weird. We'll try to walk through some of those today if we have time. Yeah, we should have time. But the final product we're going to be working with is different notation. Are you ready? The notation we're going to be using for the rest of the year. It's called the definite integral. Pretend that it's glowing and there was just a sound of angels that just appeared. Okay, this is pretty much what's happening. Not that sound. More angelic. So we've switched from, I'm blanking. Yes, Greek letters, sigma, to sum. Sigma is that thing we just wrote on the last slide. To now summa, which also means to sum, but I think it's in Greek. No, Roman. I don't know. I was never. It was all Greek to me. I don't know. All right, we're going from A to B. Now I see where my son gets it from. I apologize. I'll talk to myself. You're being annoying. Stop telling these jokes. It needed to be done, right?
Not a self-reflection.
Now I'm like, huh?
You got a self-reflection.
Yes, I'm realizing I am the person I need to be talking to. Wow, this is a day. This is a life changer right here. Jackson, you should have been honest with me all along. All right, so no longer are we talking about delta x sub k's. This is going to get kind of existential here for a minute, and I may enjoy it. I don't know if you guys do. Do you know how we had x sub 1, x sub 2, x sub 3, x sub 4, and this would be the partitions for our left or right or midpoint Riemann sums, right? Now, imagine 10,000 rectangles on this interval from A to B. Imagine 10,000 rectangles. Is there still a delta x sub k? If there's 10,000 rectangles on that interval. Yeah. Right? B minus A over, did I say 10,000? B minus A over 10,000. So if I go from 0 to 1, just as an example, if I go from 0 to 1, I would do 1 minus 0 over 10,000. Every rectangle is 1/10,000th of a unit wide. How many numbers are there between 0 and 1/10,000th? Infinitely many numbers. Okay, let's make 100,000 rectangles. Now 1/100,000th is our width. How many are there between? How many new rectangles could I make even on that interval? Infinitely many. Well, wait a minute. What if I say there's infinitely many rectangles? Guess what just happened to every... Now this is going to get, again, kind of existential. Is there still a left endpoint or a right endpoint on every subinterval? If there's infinitely many rectangles. What do you call them? What's it called when you partition this line into infinitely many parts. The real number line. You ever thought of it that way? What goes on the real number line? Okay, give me some examples. Have you ever stopped and thought about all real numbers? Stop and think. This is nerdy, but this is a safe space for nerdiness, okay? 0, 1, 2, 3. Those are the counting numbers. Integers. And they're negatives, right? Let's just pretend the positive integers. 0, 1, 2, 3. Okay. 0 to 1. 1/16. 1/8. 3/16. Every fraction would be fractional real numbers. What are we missing? What are we still missing? Irrational numbers. Okay? Beyond 1, or between 0 and 1. Radical 2. Is radical 2 a fraction? No, it can't be written as a fraction. It's irrational. Radical 2, radical 3. Okay, let's put all those on the number line. Are we getting there? Yeah, because the counting numbers and all the fractions, they filled most of it. We also needed the irrational numbers. Do you see how we're filling up every single number on the real number line? If you make infinitely many rectangles on the x-axis, every single left endpoint, right endpoint, midpoint would get mapped to a real number. Because aren't you filling every single one of them in? What did those x sub k's turn into? X's. X is a real number. We call it the x-axis. It's the real number line. Didn't every x sub k now get mapped to a specific x? Isn't that kind of crazy? Do you understand at all what I'm saying? X sub k had to follow a rule. Every 1/8, 1/16, whatever it was. X is every real number. Okay? Fractions, rationals, fractions, irrationals, everything. So f of x, man, we've been dealing with that for a long time. We never really stop and really think about what it is. It's a function of a x value, specific x on the real number line. This was crazy because no longer are we talking about rectangles anymore. There's a process that goes with this, okay? Here's the setup. Here's an example. It's easier to explain what it's telling you to do. Just like d dx of x squared told you to take the derivative of x squared with respect to x, yes? This tells you to find the area under x squared on the interval from 0 to 2. And when I say area, I mean between the x-axis and the curve. When I say area under, I'm going to misspeak a lot because that's just calculus terms. This calculates the area between the curve and the x-axis. That would be negative x squared. It'd be between the curve and the x-axis. Does that make sense? This process we're going to learn is going to calculate not approximate area, exact area, and I'll say under the curve, but understand it's always between the curve and the x-axis. Okay? As long as the function is continuous. If it's continuous, then it is integrable. All right? All right. But first, we're going to practice converting with notation. Can you guys read that in the back? You can read that? Okay. The interval -2 to 4 is partitioned into n subintervals of equal length where delta x equals 6 over n. Where did that come from? 6 over n. B minus a, 4 minus -2 over n, right? So what's the width of every rectangle? I'm being redundant here. 6 over n, right? If there's 100 rectangles, 6 100ths is every width of every rectangle. But we're making n go to infinity. So that width is pretty much 0, which is good. That means there's more rectangles on the interval, right? And n is going to infinity. Let m sub k denote the midpoint of the kth subinterval. I'll be honest. If we're making n go to infinity, it didn't matter if it's the midpoint, left endpoint, or right endpoint. Because how many are there? Infinitely many. Doesn't matter. All right. Express the limit as an integral. All right. So we're going to need an integral symbol. Part of your homework is going to be to practice your integral symbols. Which are nice. Orchestra people. Keep it clean. Okay. But what does it look like? You should recognize this. The what?
Oh, cool.
No.
Cool.
No. Give me a minute.
Oh, it's on the actual.
On.
Oh,
Watch here. That looks like the apple. Violin. See it? Shh.
oh, cool.
It's been there all along. Been there all along. Right in front of you, cellists, violinists, violists.
Whoa.
Man, nobody likes the violists. Any viola players in here? Very good. Aren't people? Isn't that a normal thing in orchestra to take the viola player? Okay, I thought so. I wanted to just cut it. I wanted to be cool there for a minute. All right. Integral from what goes in the bottom? -2 to 4. That's your interval. Make sure you keep those straight. The order matters. -2 to 4. All right, wait a minute. What's going on here? We got 3m sub k squared minus 2m sub k plus 5. Do you understand what that means? -2, 4. Let's pick a rectangle, any rectangle. There it is, boom. Isn't m sub k the midpoint of that interval? You with me? M sub k is the midpoint of that interval. How many m sub k's are there if n goes to infinity? Infinitely many. I drew it really wide. It's not that wide. It's infinitely narrow. There's infinitely many m sub k's. Let's not call it m sub k anymore. What's the name that we talked about today for infinitely many values between -2 and 4? The m sub k's turn into x's, don't they? So this is really 3x squared minus 2x plus 5. And our delta x, there's no longer really any width because there's infinitely many rectangles. So it turns into dx. Do you remember what dx was? I'm not the nerdiest, most intelligent mathematician. Okay, so sometimes I explain things in simplistic terms. When we talked about dy dx, what did I tell you dx was? The smallest possible change in x. Good. Okay. Guys, isn't dy the smallest possible change in y? Isn't change in y ever change in x slope? We want it to be exact slope. It's the smallest possible change in y over the smallest possible change in x. It's the smallest possible window you can imagine. But it's still a rise over a run, isn't it? But isn't dx the smallest possible change in x for that to be the case? Well, wait a minute. We're multiplying a height times a width. Oh, area. But it's not really a rectangle anymore. It's almost like a sliver. I mean, think about it. I know I'm kind of over-explaining this. What would it look like if I were to draw infinitely many rectangles in here? Solid. Very good. And specifically, you ready? That, and then what? That? Ooh. No gap. Pretend you didn't see that. Ready? Solid. Solid. It's like back when you got really bored in freshman English class and you drew a picture and you wanted to shade it and you just drew a bunch of lines. Remember doing that? It was just me. I don't know. Romeo and Juliet. I kind of lost track. Remember? Did you ever do that?
Etch a sketch.
Maybe it was me.
I do the etch a sketch.
Yeah. If you draw enough vertical lines, you're going to shade it. You're going to shade the exact area as long as your pencil is, the graphite is infinitely narrow, right? I mean, you get where I'm going here? We just made infinitely many vertical lines here. And it's going to shade this area beautifully. You don't necessarily need parentheses here. The dx kind of just goes off to the side. This is commanding you. It's telling you to do something. Find the area under this function from -2 to 4. Does that make sense? Excellent. Now, just for fun, wasn't planning on this, but whatever. Story of my teaching career. If you have a calculator, you're welcome to join along with me. It was worth a shot. You guys have this written down?
Yes.
Yeah.
I'll forget it. 3x squared minus 2x plus 5. So how about that winter storm coming?
Excited.
We'll see. Who has run out of room to put snow at their property? I'm about out. Cole with a K.
Place a bet on what the answer is.
You're playing a bet? Placing a bet?
Place a bet on what I think the
What do you think?
90.
90. Anybody else?
91.
Yeah.
I'll take 89.
I think 90 is a good bet.
91.
All right, so this is kind of cool. The button to the right of the 9 is the templates button. And there is an integral symbol. Now, there's one with no bounds on it. We want the one that has bounds with a spot for -2 and 4. 3x squared. Was it -2x?
Yes.
Plus 1?
No. Plus 5.
So close.
Plus 5 dx. Cool! With a K. Cool.
Wait.
I'll take it.
Worked in my head. 90. Wait a minute. That graph has an area of 90, like exactly 90? That's crazy. That's kind of cool. What about from -4 to... Worth a shot.
Pi.
To what?
Pi.
Pi?
Whoa.
E?
No, wait, it's 90.
Any guesses on this one,
I
Cole?
was hoping we'd choose a real number so I could, but I'm not doing pi.
All right, that is approximately 58.845. That's cool. Like exact area. Okay? What's the conversation going over there?
Truncated.
Would you truncate it? And honestly, it makes me upset for you guys. I'm being honest here. It makes me upset that they truncate your grades. Why? Like, we have the ability. We have math. We have programs that have like computer programs. Why can't they round it? Or take it to the 10th place? You earn those. Again, I would protest. I want my decimals back.
You're right. Ryan's on notifications. Ryan's on
Did we have this conversation already?
Yeah.
Okay. I'm still upset about it. All right. So here's the cool thing. I want to visually show you. Menu, analyze graph, integral. -2 to 4. Boom. 90. So that's the area it's finding. Put that in your mind. It's the gray shaded area. Can you see it? That's what it's calculating. Cole, how did you calculate that?
I found the antiderivative and I found the difference between the antiderivative f value of -2 and 4.
Want to teach?
Sure, why not?
This is what is going
He even caught it. I was hoping that we could laugh at him for something.
Ouch.
This is definitely a second year taking calc.
You got the notes? Did you take calc last year, Cole?
I did not, no.
It's a lucky guess.
So lucky,
Over the
guys.
weekend? Did you do a little studying over the weekend, Cole?
No, but I watched the video because I missed you guys.
Oh,
How do I get back to the pen?
You click on the pen.
Thank you.
Left.
Like right,
No.
like right above, like right where you.
Nope.
No.
He's bad at technology. He's bad at technology, though.
Right below the arrow.
There, found it.
Yeah.
Luck blue.
Everybody laugh. Easy.
There's your opportunity.
Might be good at calculus. You're on smartboard.
Do I need to show my work to find the antiderivative, or can I just write the antiderivative?
Kind of do it quickly. You can do it. Okay. I was really playing. It was not in the lesson plan. I kind of wish I was that teacher for once.
It's more fun.
Who are your teachers that you know like right at lessons?
4 days.
I go on the homepage and
Yeah.
Friday. I'm like, bro, relax. Stu definitely.
Remember that conversation we had about during Beckenham?
is like 5 YouTube videos per
Do you remember when we had that next little conversation back there during the Beckenham? Yeah.
Nicole, why are you taking the antiderivative here?
So I was bored one time, and I decided to find out if the difference of the antiderivative at these two values at antiderivatives f of 4 and -2 for different. I did actually f equals f is x squared. That's horrid. But I did it between 0 and 2, and I found out the area underneath of that curve is equal to the just using Riemann sums, about approximate. I found it was equal to the, what was it? Equal to the or the difference between f of 2 and f of 0 was equal to the derivatives. 2x. So I just used a graph kind of
Yeah.
where that'd be a rectangle just from 0 to 2. That's a rectangle of a height of 2 would be, no, it's a triangle.
Can I help you?
Go ahead, yeah.
Cool.
It was a while ago that I
It
thought of
almost
this.
looks like when you guys did that driving activity. Remember that driving activity?
Yeah.
Oh, those were good times. It's almost like you took your rate data, like your velocity data, and when you add it up, if you add up all the velocity areas, like the areas under those data points, the area under that velocity data what would it mean? What would the units be? Oh, distance in miles. So the area under a velocity curve would be miles, which is the antiderivative of velocity, isn't it?
Oh my gosh.
Antiderivative of velocity. So if you're trying to find the area under some random old curve, it makes sense that the area would be the antiderivative function, miles. So maybe we should take antiderivatives to do this. I see what you're saying, Cole. That's kind of was just dawned on me.
You're
I like it. So area. Let's talk in general. You can have a seat. You can walk here. I'm going to stand up there.
I'm all right. Thanks, though.
Area is. You guys see that negative sign up front? You see that negative sign up front?
Yes.
It's the opposite of the value of the integral. Now, be careful here. All this is trying to say. Back up. The negative sign will work itself out with the math when we do it tomorrow. Okay? The negative sign will work itself out. It's just, what if you see an area under the x-axis? It will be negative. I'm a visual person, so let me show you. Huh?
My work. It's gone.
Do you remember the negative x squared graph we talked about? Yes? From 0 to 2. That will work out to be a negative area. I want to say negative 8/3, but I don't remember for sure.
It was a third.
Thank you. That area will be negative 8/3. There are times on the AP test when they will do this. Because you know how, like, you've heard in math before, area can't be negative? Yes? They may call it an area of 8/3, but it's below the x-axis, so it has a signed value, an integral of negative 8/3. Does that make sense to you? All right. Another logical question that I would ask, or a student might ask, is what if the function can't make up its mind? Ready? Positive area is 2. Negative 3. What's the integral from A to B? Or not to be. I mean, it could be later on. C, maybe. What do you think? I hear 5. I hear negative 1. This is so much fun. You ready? I'm going to walk in front of you again. This is what I do. My velocity is positive. I started it at a position of 2. Keep that in mind. Positive velocity. negative velocity. I stop at 0. How far did I walk? What would you need to know? Yeah. Okay, how far did you walk to the right? How far did you drive? 3 units. 3. No. 2. I walked. How far did I walk back? 3. Where am I? I started at 2. I walked to the right. 2. I walked left. 3. Where am I? 1. I'm 1. I've been displaced -1 units. Do you agree? The area under our velocity curve is displacement. But where did I start? I started at 2. So I've been displaced -1 units. Where am I? -1. Are you with me? The integral finds displacement. The integral finds displacement. Does it make sense? It's about to get real. Okay? For homework, you're going to do LRAM 30 on your driving activity and RRAM 30 on your driving activity. My hint to you, you're going to want to convert your 10-second intervals into hours so that you can get, you have miles per hour listed, you have seconds, you want to have hours. It's not a hard conversion. Your calculus students figure it out. Also, for homework, I don't know that I'm going to give you all that. We'll see. You're going to convert on page 282. Everyone that I circle, please. 3 is a conversion problem. 6 is a conversion problem. What are all the C sub k's or M sub k's going to turn into? X's. Very good. 9. Now listen. 9, 12, 15, 18. Do not use your calculator. Okay? It says use a graph. So you're going to look at the area and you're going to say, oh, that's a semicircle. Or, oh, that's a triangle. I don't know how to do this in a calculus way, but I'm going to look at the graph and use a geometric formula to figure that area out. Does that make sense? Are you with me? So I guess most of these. So 9 through 18 multiples of 3, 3, 6, and 9 through 18 multiples of 3. And then LRAM 30 and RRAM 30. There are 30 subintervals on your driving activity.